Howdy, my name is David Alfredo Gonzalez-NARVAEZ. I am an undergraduate chemistry student from the University of Puerto Rico at Cayey. During this summer, I have been conducting computational chemistry research in the form of molecular dynamic simulation study of solutes in deuteric solvents, or DES, at Texas A&M University in Dr. Daniel Tabor's lab. What are DES? The DES are homogeneous systems composed of two or more substances. A homogeneous mixture is a gaseous, liquid or solid mixture that has the same proportions of its component throughout a given sample. It is uniform in composition throughout. There is only one phase of matter observed in a homogeneous mixture. Examples of homogeneous mixture are air, cup of coffee, and detergent. The name of DES arises because the melting point of the mixture is lower than the melting point of each of the pure individual components. The melting point is the temperature at which the solid and liquid form a pure substance exist in equilibrium. DES are obtained by mixing a quaternary ionic compound which acts as a hydrogen bond acceptor, or HBA, with a metal salt or hydrogen bond donor, or HBD. HBAs are chemical species that can accept an hydrogen. On the other hand, HBDs are chemical species that donate a hydrogen. As an example, in the diagram shown, the oxygen atom of the hydroxyl group is called a hydrogen bond donor because provide an intermolecular hydrogen side to nitrogen, and the nitrogen atom is called a hydrogen bond acceptor because it is accepting the intermolecular side of hydrogen from the oxygen. This electrostatic interaction is called a hydrogen bond, and it is a transient interaction that occurs at the intermolecular level. In other words, no bond exists between the atom of the HBA and the HBD. As an example, substance A and substance B don't normally mix. When you combine them, you end up with an heterogeneous mixture that exists in two separate phases. However, if the mixture is heated to a temperature of 80 degrees Celsius, we obtain a stable homogeneous phase where a uniform solution is observed. By mixing them, we obtain a non-toxic and clean mixture that will be the DES. Moreover, this homogeneous solution has better properties than the separate substances. DES can be considered a greener solution due to the lack of byproducts and thus the conservation of materials when making them, as well as their low volatility and the fact that they can easily be made from constituents that are non-toxic and pose no threat to the environment. For that reason, deuteric solvents are of great interest as they are established as clean mixtures and meet the requirements of green chemistry. These systems provide tunable properties attractive for their ease of preparation and lack of need for purifications, depending on the type and the size of groups added to the primary structure of your DES components and the ratio of the component used. You can tune properties such as the melting point, viscosity, and conductivity. The aim of my work is to employ computational chemistry methods to model derivatives of phenotized molecules. The phenotized molecules, it is composed of three ring structure in which two benzene rings are joined by a sulfur and a nitrogen atom in non-adjacent position, and tempo, a common radioactive organic molecule. In a DES, to try to have a better computational understanding of these solutes, so that we can both understand the behavior of existing solutes within DES and predict new compounds that have the potential to produce useful properties superior than existing compounds. It should be noted that the main limitation of DES is that there is a lack of both experimental and computational characterization data. There is no constant pattern in their behavior. Therefore, it is difficult to predict their physical properties. To overcome this problem, exploratory pathway must be developed to create a method can be used for the understanding the physical properties of DES. The main difficulty is due to the complexity of molecular interactions in TES. This complexity has stalled efforts to understand the relationship between structure and function. Thanks to NSF for funding this research experience and Texas A&M University Chemistry Department for the opportunity to provide a space for its development. Thanks to Dr. Daniel Tabor's research group for providing support. Thanks for my mentor Abigail Moody for her support in this research project. Thanks to all of you who are watching this video. I hope it's helped you to have a better understanding of the eutectic solvents.